Electrostatics 10. Today's lesson is on electric dipole. See, we were talking about electric fields of various things like a single point charge, and then continuous charge distributions we found out. But one important point, one important idea of dipole is very crucial in chemistry, actually speaking. Simply speaking, if I ask you what is a dipole, what will you say? What is an electric dipole? What would you answer? Given some freedom to you to say whatever you want, tell me something. The single unit consisting of a plus q and a minus q bound together. Okay. You are free to raise any very fundamental doubt as well. Same charge with opposite signs, somehow bound, I told you. In the figure, we did not show how they are bound or whatever. If they're left free, they will come and attract and hit each other, right? So something more we require to tell they are bound or whatever. That when you talk of molecular dipoles, chemistry will take care of it. But right now, in a physics lab, you would like to produce a dipole. You might take two small spheres, somewhat separated from each other widely, little large distance you require, and some insulating connection you can have, insulating rod in the middle. Why? Because charges should not flow from one to the other. Give some plus charge rate, that means electrons were removed. Give some minus charge rate, some electrons were added. Somehow you saw that the charges were same. So this will be some dipole you can create in a physics lab. But that kind of a dipole is not very important. Maybe it's important somewhere in some kind of an industry. I'm not very sure. But molecular dipoles are important. Isn't it so? So molecular dipoles are important. Could you tell me what a molecular dipole is? Or dipoles at a molecular level are important, in other words. Can somebody tell me whether they knew any dipole previously in chemistry? Water molecule is a polar molecule, you say. Water molecule is a dipole. Like if you have a glass of water like this, this is some water in a glass, for example. But this is for a normal eye. You say this is a glass of water when it is placed on the table. But when you look in terms of a physicist viewpoint, remember, I'll imagine there to be many dipoles, randomly oriented. So, in other words, from a physics perspective and in an electricity perspective, if I look at a glass of water, I'll visualize many arrows which are oriented in a very random way inside the glass, inside the water, or inside the glass. Instead of having water molecules there, or water which is, you cannot differentiate between one and the other but for a naked eye, right? But in a microscopic sense, you can always think of many water molecules making bonds with each other, right? What do you say? H2O, H2O, H2O. Once again, a bond between each molecule you have there. Are you okay with water molecules chemistry? I'm not sure. So, but from a physicist viewpoint, when I look at a glass of water or a bottle of water like this, I'll think of many dipole moment vectors, though they are arranged in a very random way and producing no electric effect in bulk for the water. No electric effect means the net charge would be still zero. But I imagine many arrows, all arrows jumbled up inside the bottle. Why? Do you have any idea? One oxygen molecule, another hydrogen molecule, another hydrogen molecule, will say making a bond like that. And you also know the bond angle to be some 104.45 or 5 degrees. If I'm wrong, correct it. This is oxygen, this is hydrogen, this is hydrogen, isn't it? Huh?
Yes, sir.
And we say oxygen has more electronegativity, so the electron pair, the shared electron pair is pulled more towards oxygen, we say. So we say minus delta partial charge is formed there, plus delta formed here like that. Or for this case, I'll say minus delta by 2 plus delta by 2 here, minus delta by 2 plus delta by 2 like this, I'll say. So as a whole, there will be minus delta negative charge plus delta positive charge plus delta positive charge. So there are two dipoles here. This dipole moment direction is from negative to positive. P. This is another P, dipole moment vector, that is delta into the bond length. How many angstrom units? I'm not sure. Whatever it is, that will be defined as P. And the direction of such dipole moment is given from minus to plus. So this is having two dipoles here, resultant of which is like this. This is what I mean by an arrow here for water. So this arrow is a dipole moment vector. This is dipole moment vector. I don't remember the bond length. You can refer. Bond angle, 104.45 or 104.5 degrees. Just check once again. Correct me if my memory is wrong. So there are dipoles practically, and especially dipoles at a molecular level are very important. And of course, this water molecule will make a bond with another water molecule. That's once again. We
Sir,
talk about
bond
other
length
bonds.
will be 95 picometers.
950.
95 pm.
95. This one.
Yes, sir.
Okay. So some 950 angstroms, I remember. Okay, whatever it is. So that is a bond length. So dipole moment is what? This partial charge plus delta by 2 minus delta by 2 into what? The bond length. So it is, see, I don't know whether you understood now. I've just made it a little more physics oriented. Can I believe that you followed something here? Or you added something more to your chemistry knowledge? Tell me. Or is it contradicting what you learned in chemistry? Hello? Or you forgot everything in chemistry? Or you don't think physics dipole and chemistry dipole are not same? Tell me, Aryan. Siddhartha Gaud entered the waiting room. Who is the Siddhartha Gaud? Is there any fellow whose father's name is that? I'll just allow him and ask him. Yes, Siddhartha Gaud, who are you? Quick. Siddhartha Gaud. So that fellow left. Okay, good. So, yes. Who are you? Siddhartha Gaud, who are you? What name is this? There's no Siddhartha Gaud in my class. Come on, quick. So, shall I remove you? If you're not identifying yourself, I have to remove you. I thought you my student only, but entered with a different name, so I allowed you. He left.
Yes, sir.
Okay. Now, is it all right for you? Do you remember anything of this sort or not in chemistry?
Yes, sir. Dipole interaction force.
That is for when you take one more what you call water molecule.
Yes, sir. Between two whatever.
But right now I'm just talking about a single dipole here. The H2O molecule is a dipole. Do you agree? Rather,
Yes, sir.
H2 has two dipoles in it, which we put as one dipole in this direction.
Yes, sir. The net resultant
Dipole moment, that is resultant dipole moment. Actually, look, chemistry, if you connect a little physics, not much, life becomes very, very simple. But some more people don't think chemistry and physics can be connected. It's not connected. It is same thing. Try to understand. Like, what is a bond? I asked. How do you think a covalent bond forms and exists? And what is that bond thing actually? Who is bonding what? The electron, at least in your own language, for stability's sake, they would like to have, say, 8 electrons in their outermost orbit, right? Hello?
Yes,
Are you there, children?
yes, sir.
Yes, sir. So the 2 electrons, now they don't belong to this atom or that atom, they belong to both the atoms, we say. But remember, these 2 electrons which are shared will be pulled by the positive ion core of this, positive ion of core of that equally. That's one when you have a covalent bond. If one of them pulls more, it becomes a polar. And you say electronegativity, people say. But a simple attraction between positive and negative charges, if you think, that looks so simple. Hello?
Yes, sir.
A silicon atom, for example, because we'll be, I think you've done some kind of a, what you call, semiconductor physics also, haven't you?
Yes, sir.
A silicon atom, for example, what is the, how many electrons are there in a silicon atom? 2, 8, 4. Isn't it? Yes. Hello.
Yes, sir.
So these 4 electrons are in the outermost orbit. Total remaining thing we call is a core. So plus 4 core here and 4 electrons outside. This is how you show things. I really don't know whether you understood what this core thing. Now one more silicon atom comes, right? Even that has y plus 4 core. Do you follow that? If you remove these 4 electrons, ultimately what will happen? Remaining, you got 14 protons and 14, 10 electrons. So 4 plus 4 will be the net charge inside. Hello. So when you
Yes, sir.
say a covalent
Yes,
bond is
sir.
formed, these 2 electrons are pulled equally by these cores. So that's what you mean by a bond. Do you understand? Hello.
Yes.
So chemistry becomes simple, interesting if you really understand that way.
Okay. Sir, so it's not just the sharing of electrons, but how much it is being
What do you mean by sharing
pulled
of
by.
electrons? Isn't it look silly if you say simply sharing of electrons?
Yes, sir.
Well, bond is a force. Try to understand. Everything you should be reducing it to force and energy, children. Sharing is nice. Sharing is good. From the day one, we tell children, come on, when you have some something to eat, share with your friends, we say. That sharing is nice. But physics has no emotion there, you tell me. Do you understand what I told? I remember one fellow
Yes, yes.
asked chemistry, sir, I will tell you. I was just talking in these terms, and that fellow did all his chemistry just with the small ideas. I mean, it makes sense for what all you observe in chemistry in an empirical way. Do you understand what I mean to say? There you take it just like that. They share, so there's a covalent bond. This electron now makes 8 electrons here. That electron makes 8 electrons there. Whatever you say, right? Isn't it so? One more silicon here, one more silicon around here, one more silicon here, one more silicon. Finally, 8 electrons in the outermost orbit. Stability. So these words are nice, but there's much more, not much more, little more in terms of forces. So do you understand what I speak now? These 2 electrons are pulled by
Yes.
the 2 positive cores equally.
Equal.
Like for example, I hold one end of a rope and you hold another end of a rope and we pull, right? Do you follow? So tension develops. So here electrostatics force only, but we don't use these words because NaCl we say electrostatic. This is covalent. Ultimately, it is a force between charges. Do you follow? Hello. Now,
Yes, sir.
now even electronegativity can be understood like that, but in chemistry it's more empirical. They give a scale. Electronegativity for fluorine, highest some number 4. I don't remember from intermediate.
Fluorine.
And then some cesium or something least. Some numbers they give, no? Hello.
Yes, sir.
Yes, sir.
No meaning for your chemistry. So there, that is an empirical approach. That works. There's no problem. There's nothing wrong in it. But what I was trying to tell you is physics makes it more simple. The way we look at it is all the time like that in terms of forces and energy there. So whatever you told there makes sense. Now, what is this H2O business here? In silicon, of course, they're pulled equally. But in the case of hydrogen and
Oxygen pulls more.
oxygen pulls more. Why?
Its electronegativity is higher.
Electronegativity is higher. Means what is electronegativity? What is electronegativity? Whatever it is, okay. Electronegativity, it pulls. Once again, you can understand it in terms of force only. So oxygen pulls it more because of the, once again, remember, other than the electrons, what is remaining is the positive ion core. There, of course, you've got 6 means you've got a what you call bigger positive core than compared to hydrogen. So that will pull more. So simple. Hello.
Yes, sir.
And of course, the bent shape comes because of the what you call 2 electrons will be shared, no? you say they participate in bonding, and there are 4 more electrons, right? You call them what pairs? Lone pairs, huh?
Yes, sir. The 4 are 2 lone.
Even that bent shape is also because of the repulsion between the unpaired, that lone pair of lone pair electrons. They repel, so they try to go as far as possible, and it happens when they bend. It's very interesting. Yes. Chemistry is so interesting if you include forces. Do you know? All right. Anyway, we are deviating and we're falling behind. But what I was trying to tell you was, water molecule is an electric dipole. You just stick to the same idea only. Oxygen has got more electronegativity, therefore it pulls the electron pair more than, the shared electrons more than the, what you call, this hydrogen. So this side is left made positive, that side is made negative, right? So this is now a dipole. And also, I don't know why, what is the meaning of people saying in chemistry the dipole moment direction is from plus to minus. I really have to see, but it is actually, I'm talking about the dipole moment direction, dipole moment vector's direction. They say some positive, negative, no? Isn't it? Hello?
Yes.
No reaction from you people. But remember, the direction of dipole moment is from minus to plus. I'll be showing it more mathematically soon. Okay? So, and remember, all this is important for me in physics to explain you later the effect of a dielectric when you place that in the space between the 2 plates of a parallel plate capacitor. Hello. So just don't forget, these are all nice ideas. So yes, dipoles are there. You can make some dipole in a physics lab like this, or you already have naturally formed dipoles. Okay, like water, the most important thing.
Yes.
Right. Now, I'll continue. So a dipole is a single unit. Try to understand. Single unit consisting of a plus and minus. Look, when a plus sits over a minus, is there an electric field around it? I'm saying you, a plus charge sits over a minus charge, equal minus charge. The electric field around it is what? No electric field, zero electric field. This will be the direction of E of plus charge, and this is the direction of E of negative charge. As a whole, no field outside. Right? But the moment you separate charges, field forms. This is separation of charges. Forms a field. So when I said dipole is a minus charge and plus charge somewhat separated like this, there should be electric field around it. Okay?
Yes.
There should be electric field around it. So as we continue from a single charge as a sequel to this kq by r square. Now I would like to find out what could be the field strength of a dipole around it. My main aim is that once I get convinced myself that there are dipoles, what do you mean by there are dipoles? There is a single unit existing as one entity which has got a plus q and minus q. If we are ever in a doubt, we can go to chemistry and see that yes, H2O is a dipole. And you can also form a dipole, like 2 spheres you take and rub them off and get some positive charge for this, equal negative charge for that, and join them by an insulating handle. That can also be talked as a dipole to look directly. So yes, after that we need to find out the electric field of this dipole. That's my main job. Hello?
Yes, sir.
Now, but before that, before we went for that, we would like to define another physical quantity, new physical quantity. That is electric dipole moment, P bar. After defining P bar, we'll go for finding out the electric field of a dipole. Okay. Can Sriya summarize what all I talked until now? Because
Yes,
maybe
sir.
many are sleeping. I want them to get up and listen to me. Come on.
So first we defined a dipole. We said that in order for a dipole to be there, there must be same charges, meaning same magnitude and opposite
Opposite in signs.
charge
That
signs.
actually
Yes. So
you might get it out. Why only this one I should call a dipole? Can I not have a dipole with plus q or something like that? That's not the correct case. These are practically existing units. Okay.
yes, sir. But in order for the field to exist around it, the charges must be separated.
So since
Because
in a
if they
dipole they
are
are already separated.
uh, yes, sir, since in a dipole they will
No,
be
there should be a
separated,
story.
there
You
will be
cannot talk, disjointed things. We said a plus q minus q existing as a single unit is a dipole. Dipoles are practically there. Molecular dipoles are very important. H2O water molecule is a dipole. For a dipole, there will be a field around it. Why? Because had this plus and minus been on one over the other, the field would have been zero. But once in a dipole they got separated, there should be a field around it. So like we found out the field of a single charge kq by r square, we would also like to find out the electric field of a electric dipole. But before doing that, we require one more physical quantity called electric dipole moment. Do you understand?
yes, sir.
I've taken so much time to make things meaningful. Now, in that connection, we write behavior of a dipole, electric dipole, of course, in a uniform electric field. When we do this, we come to define, or we go to define electric dipole moment. What is this heading? Behavior of a dipole, an electric dipole in a uniform electric field. What is a uniform electric field? E, the value of E is same all over in that space wherever you consider. That's called uniform electric field, which is shown by parallel field lines I told you. This is one uniform electric field, and in this uniform electric field, think of suspending one electric dipole, like a plus charge here and a minus charge there. If you think, come on, what is this dipole? I've not seen. What is this? How do I suspend all that? If you think, practical things are there. Like a parallel plate capacitor will be there, which means two plates which are oppositely charged and placed at some distance from each other. In this, I go and place a tumbler of water. I told you already, water molecules are all dipoles. So this electric field applied here will do something to the dipoles inside. So it is very, very practical. You know, hello, do you follow? Each dipole is bound to the other dipole here. H2O molecule is making some kind of a bond with another H2O molecule, isn't it?
Yes.
Hello? Huh?
Yes.
So this is not a free dipole like this, practically speaking. But for our discussion, it's okay. You think that there is one E like this, huh? Which is probably here formed in between the space of two oppositely charged metal plates, which are together called what? A capacitor. Hello? Huh?
Yes.
So in such field, we suspended one dipole. Here, practically just having one molecule and suspending it doesn't work. There will be many dipoles here, which are there in what? Not which are there in water. Water itself is a combination of many dipoles. So once electric field is applied, since dipole have got a plus q minus q charge, they experience a force, right? Let us look at it. What will happen here? This will experience one force like this in this direction. Hello, are you listening?
Yes.
This is a plus q charge, so it will experience force in this direction. This will experience force in this direction. So what would happen? The net force would be 0 because this is q, this is q. Force is eq this way, force is eq this way. So two equal and opposite forces produce no force. But if they're not acting along the same line of action, they produce a torque. If two forces act along the same line, the net force is 0, net torque is 0. But now one EQ acts like this, another EQ acts like this. So they don't accelerate the dipole center of mass forward or backward, but they turn the dipole. Okay, I'll show a different position now. This dipole might have turned like this. Sorry, this charge, this minus might have turned like this. So this is how my dipole turned. Because of what? An EQ force acting this way. This is a positive charge. Therefore, E will apply a force in the direction of itself. Right?
Yes.
And on this, it would have applied a force like this. EQ in magnitude. So, two equal and opposite forces. Two equal and opposite forces acting along two different lines of action. Acting along two different lines of action produce what?
Torque.
The torque. Okay. For torque, there should be an origin O. I'll take my origin at the minus charge O. And I'll define the length between them as a vector now from the origin O away from it. This is L. Okay. Hello.
Yes.
This is the origin. Torque will be about an axis passing through an origin there. So this is my origin for taking torque. I take it here for my convenience because torque of EQ would be 0. There will be torque of only this EQ. Hello.
Yes.
Tau bar equals R cross F, right? Huh?
Yes, sir.
If I can follow an IJK approach here, easy one, not to get confused. Here R bar means what? L bar, right? L bar equals,
E.
like if this angle was theta, because I defined my direction of L from O to this L is a vector, I told you is a vector. This angle, let me say, is theta. Huh? So this distance is what? And this distance is what? Can you tell me? If this is theta, hello, this is theta, this is 90, this
The
is
above
theta.
angle will be theta. Yes.
So this is L
Sine.
sine theta, this is L cos theta, right? Hello.
Yes, sir.
Yes,
So
sir.
if this is my origin, what is L bar now? Model cos theta
Plus
I
model.
cap plus model sine theta
J cap.
J cap. And F equals how much here? This F you don't require because this is about this point only. Only this one you require, isn't it? Huh? EQ
Yes, sir.
I bar. Hello.
I cap. Yes.
Now tau equals R cross F. Here itself you multiply. Huh? I cross I 0. Isn't it?
Yes, sir.
Huh? This one. L sine theta. So what will I write? EQ model sine theta into J cross I. Isn't it? So minus K cross EQL sine theta will be the torque. That means the torque as a vector is into the plane here, or a plus sign we can show. Plus sign is the tail of an arrow, I told you many times. So the torque is into, means rotation is clockwise. Now, what does it mean? Because of this torque, the dipole is going to turn in the clockwise direction. Torque as a vector is into the plane. Do you follow? This is my tau vector. It says this is given by the maths itself. And physically also, you know, once this is turned this way, this turn this way, is turning in clockwise direction only, isn't it? The whole dipole. Hello.
Yes, sir.
Tell me, children. Hope you all followed it properly. Now, anytime something comes like this, AB sine theta, we get an idea that I can express it as a cross product, right? A cross B. Huh? So here Q EQL sine theta we had. Okay. This QL was defined as P. Huh? This can be written now as by defining mod P equals Q into L by defining P is what? Electric dipole moment. How are we defining it? Charge into length between the charges. Okay. So tau can be written as P cross E, where P bar equals minus QL bar. Tell me. Sorry. Minus QL bar or QL bar? Plus QL bar. Tell me, children. Hello. So P cross E will give you the torque. A vector P like this, a vector E like this. So P cross E, right hand thumb rule. P to E you turn, the thumb will go inside. This is my thumb. So if I define P as Q into L, what do I get? I don't know. People are not responding. I'm worried. E equals here this is P. I told you P sine theta minus K P sine theta, which means P cross E should be into, isn't it? Therefore, I made it as P cross. P cross E direction is only into the plane. Hello.
Sir, sir, so here instead of defining torque by force, we're doing it with electric field strength.
Can you tell me again?
We're defining it torque in terms of E, no, sir.
Torque in terms of E only. Why?
Cross E. P cross E. So, like, instead of defining it in terms of force, we're defining it in terms of.
We found out in terms of force only. We found out in terms of force only. Remember?
Yes, from there
that
only we
from the force Q was taken and multiplied with L, and we gave it a different name.
Yes, sir.
It is still that force only. You see, if you write P as that one, you will get force only. Force into R cross F only you will get. But now we are getting it in terms of force per unit charge, and P as Q into L. So it is one and same. But the way it appears is a new quantity, electric dipole moment and electric field strength. That it will be like that in physics. Remember it. This is still, we have not deviated from torque as R cross F. Try to understand.
Yes, sir. I meant like also in this way we're writing it.
Yeah. So dipole moment direction is what? In the direction of L. Do you know? Hello. QL.
Into the.
No, P's direction is from minus to plus. Torque is into. I followed a mathematical approach so that you'll follow it easily. I did not go for force into perpendicular distance like that. I just went by IJK and showed you that torque is into the plane. For torque to be into the plane, I should define P from minus to plus. So P cross E will be into the plane only. No, this I wrote. K is into the plane. Hello.
Yes.
Ellen.
So if you finish it, I'll continue. What Aryan? Vamshi, Shriyans, Vaishnaviyam. People are already dropping even before the class got over. I think they have enough of physics, I think, just within 40 minutes. So can I continue? Actually, there are so many questions to be asked here, like the way it is taught, it is discussion type. So certain, what you call, things will be left out for good reason, whether people would catch and ask. So that only tells me that how people are following it or not, I'll be knowing from that feedback only. What could be a question here? I decide once for all the direction of dipole moment is from minus to plus. Do you have a problem with that? If you don't have a problem, I'll create it for you. Tell me. I've not yet gone to the physical meaning of it. We'll go to that. But right now, until whatever is done, with this minus k cap EQL sine theta is written as P cross E, whether you follow that first or not. P is along the direction of L. This P minus K P sine theta I wrote also. There should not be a problem. Minus K P sine theta is written as P cross E. So you could never say it is E cross P. Because P cross E only will be into the plane, right? Hello?
Yes.
Yes, sir.
First of all, the question that why not torque E cross P doesn't arise. That's a silly question if you go this way. But there is still one thing. Here I took the originate O, this minus. What will happen if I take the originate center, or what will I take happen if the origin is at plus? That is important. Remember, once I said it's minus to plus, it cannot change if I change my origin, because this is a physics here. So whether you take the origin at middle, origin at here, the direction of P doesn't change. That's very, very important thing. You can check it for yourself. And that's the immediate question people catch and ask. Sir, what if I take the origin at plus Q? Is the immediate question people ask. But if you did not ask, I'll say this is a question there and then I discuss it. Doesn't work. It really doesn't work, because here also you're only just, different people try to catch different things which are comfortable to them. But the way it is done, the total connections between different facts we're mentioning is the story, I call it. That's very important. So we added one P, but we'll still talk about P. It's not over yet. Tau equals P sine theta, we saw in magnitude terms. To give a physical meaning for P, we'll do this. Theta equals 90, for example. And E equals 1 unit, 1 Newton per coulomb, whatever. Then tau will be P. That is Q into L. So the dipole moment is nothing. It is simply the torque experienced by dipole. Look, this is the direction of dipole went from minus to plus, which is the direction of L vector. So which is also the direction of P vector. And this is my E. I'll say E equals 1 Newton per coulomb. Okay. Hello. So EQ force at this point will be E into 1. EQ force at this will be E into 1. E into 1. E into Q, that is 1 into Q. EQ. So Q into 1 is this force, Q into 1 is this force. The distance is L. So Q into L is the torque, which is P. This theta is 90 degrees. So that is the physical meaning of electric dipole moment. That is, it's the torque experienced by the dipole when it is making an angle 90 degrees in a unit electric field. Okay. So few points to note. Dipole moment is a vector. The rules. It is P equals charge into L bar. L bar is from minus to plus, which means P bar is from minus to plus. And 3, P equals tau when E is 1, theta is 90. So, right? And of course, that P formula is, tau formula is what? Tau equals P cross E. So, this is what we have found out from this lesson. Any questions? And fifth one, wherever you take the origin O, find out torque, Now V equals P cross E only. And P is from minus to plus only. So why this P is a question generally people ask. After all, you had forces individually, why are you getting this P? Remember, something like what we call a charge is an intrinsic property of the matter, which tells you what electric force it experiences, what electric field it causes. So that we set Q. But here, when I have a unit called plus Q and minus Q, it doesn't experience a net force if it is placed in a uniform field, but it experiences a torque. So the torque doesn't depend only on Q or only on L. It depends on the product of both. So that's where the P becomes a characteristic feature of dipole. Like Q became the characteristic feature of a single point charge, which will decide its own field, which will decide the force it experiences. In a similar way, a plus Q minus Q unit existing together has two things in it: the charge and the separation between the charges. That product is something unique for that unit called dipole, which will decide what kind of a torque it experiences, what kind of energy we can store, right? What kind of a force it can experience later if the field was not uniform. So something specific to charges and their separation is defined by this electric dipole moment. Tell me. So, any questions, children?
Sir, in this slide, when we say line of action, we mean the
different line of action means, see, if I had some body here, some rod here, for example, if I applied one force this way, one force this way, the net force is 0, net torque is 0. Isn't it so? The body is in both translational and rotational equilibrium. But if we apply one force here, another force here, equal force, the body will be still in translational equilibrium, but not in now. So this F net is 0, right? But there is
torque is
F into L by 2, F into L by 2 torque equals I alpha, don't we write? Huh? So net force is 0, but net torque is not 0. That means the rod is going to get angular acceleration. The omega keeps increasing. Even here, the same thing happens. Here it is something like a rod only, but you can think at the end of the rod, this rod has no what you call mass, whatever, but there are charges here. And electric force is the one which is producing this torque. Do you follow?
Yes.
So it is just what we did in mechanics. The total intermediate phase is the classical mechanics based on Newton's laws. Okay.
Yes.
Anybody else? Others? I won't be starting the new thing. See, the way I started, you should be very careful how much ground I was developing. How much ground we developed, you need to really understand. I did a little chemistry also today. I don't mind doing a little more of chemistry also, giving a physics angle, but there should be a kind of feedback, no? You ask a sir, he will tell you. There used to be a fellow called Raghuram. He got a rank of 325 something in IIT. That fellow managed half of his chemistry with the physics ideas in terms of force and energy. It looks so simple. Not that you can completely connect it, because it's not easy, but a lot of it makes sense. The organic chemistry and that kind of this attack, that attack, this one, that one. At least you'll have some kind of a support to remember things. Otherwise, too many exceptions, too many things. That's a little. I mean, some people have a problem with chemistry that way, because they say follow this rule now, and they say break the rule, same rule later. So certain physics oriented fellows were not happy with that kind of a empirical understanding of chemistry. So they wanted to put some kind of a physics modeling there, which actually is, I don't even say it's a serious physics modeling, but it's simple force and energy approach. The simple idea that separation of charges produces electric field is enough to make many things very clear. Come on, when I say plus Q is sitting over a minus Q, don't you understand what it means? The field is zero. The moment you separated, a field forms. I want to find out the field, but I would like to define something, a unique characteristic feature of this unit that's called P. To understand P, we went for suspending a dipole in a uniform electric field. Then we defined a property for the plus Q minus Q, which is P. Now we are ready to do more things. All right. Okay, for the present, I'll stop, because however much I shout, however much I pat myself that I'm doing great physics, the feedback is important. Okay, I'll end the show for now. We'll meet tomorrow again.
Thank you, sir.
Thank you, children.